Good afternoon, students. In the last class we looked at the partition function of a system in canonical ensemble. The system was in contact with a heat bath which maintained its temperature to T, and this was done at the expense of exchange of energy. So, in this class we will start off from where we left and build a connection with thermodynamics for such systems. So, the motivation or the agenda of the lecture would be to build a connection with the thermodynamics. Now, by this I mean that we live in a world of a large number of particles where n tends to infinity, volume tends to infinity, such that the number density is a finite number. So, if you want to do an experiment on an ideal gas or a magnetic solid, you are typically looking at degrees of freedom that are large in number. And what you really measure by a probe or by observing systems for a long duration is a thermodynamic quantity, which is an average of many small degrees of freedom in the system. So, since we are measuring averages, we are basically interested in thermodynamics of any system. So, using what we developed in statistical mechanics so far, we can derive thermodynamics. So, I will start off with the recollection that we arrived at a partition function in the canonical ensemble. So, I am going to write down the canonical partition function. As the macro state is NVT, thermodynamic macro state, and we got the expression for the partition function as summation over all the micro states e to the power minus beta h, which is the Hamiltonian of the micro state. But we said that we are interested in a representation in terms of energy, not microstates, because there are many microstates which may have the same energy, so called degenerate microstates. So, we reduced it to the representation in terms of energy, and when you do that we observe that the Boltzmann factor is now in terms of the free energy, the function of energy E, okay, free energy for the internal energy E. And we said that the summation involves a large number of energy states. So, it can be approximated by the largest value in the summand, which is e to the power minus beta f, the energy which minimizes f. Okay. So, by saddle point, which was discussed, stated without proof, so, here I would like to remark that this E star maximizes the summand, which is e to the power minus beta f, and minimizes the free energy. Okay. So, E star is a maximum of e to the power minus beta f, but it is the minimum of the free energy. So, conceptually this means that if you leave a system connected to a heat bath, allowed to equilibrate, the state of equilibrium would be the state of minimum free energy. The natural evolution of a system is to continue evolving and exchange energy with the thermostat, so that the thermodynamic value of E, which is E star, actually minimizes the free energy of the system. So, the natural evolution of a system is towards the direction of minimizing free energy, and this is also what we have mathematically done here. I have said that the entire summation is contributed from the value of the summand that comes at the minimum of free energy. Now, I am going to construct the first meaningful quantity. The simplest quantity in thermodynamics is the average energy. So, why not compute something that is the easiest? So, the average energy, I will say it is E, is nothing but the expectation value of the Hamiltonian, and that can be computed by simply the average of my Hamiltonian weighed with the probability P of mu. Okay. And if I recall, this P of mu from the previous lecture is nothing but simply the Boltzmann factor e to the power minus beta h mu over the canonical partition function. And I can write this as simply minus of d over d beta into summation over mu e raised to minus beta h mu over the partition function. And finally, this can be seen to be just 1 upon z just minus 1 upon z d over d beta z, which is nothing but minus del over beta of ln z. Okay. And this is nothing but the average energy in the system. Fine. So, what I am going to do is just underline this important result. So, you can already see some kind of a building, some kind of a bridge that has been built between statistical mechanics, which is basically here the microscopic information, and the thermodynamic, which is macroscopic, where you require large degrees of freedom and averages over these degrees of freedom on the left hand side. And now we can actually find out relationships between free energy and the partition function. So, that can be done by saying that, let us say we call this expression as 1. From thermodynamics, I already know that internal energy is equal to free energy minus Ts, the elemental free energy minus Ts. So, I can write down so I think it is F plus Ts, okay, because the free energy is written as E minus Ts. So, just recall that if I take a derivative on both sides, a differential on both sides. So, small change, if I consider a small change in internal energy, then this is equal to a small change in free energy plus TdS plus SdT. Okay. But I know that from first law of thermodynamics I can write down this TdS as the pressure volume work minus mu dN plus some internal energy change, and this is the SdT. Okay. So, you can knock off the internal energy change from both sides, okay, and simply see that dF is nothing but minus PdV plus mu dN minus SdT, which allows me to write down for entropy as minus for dF by dt at constant NV conditions. Okay. What do I do with this? Well, I am going to substitute what I have just obtained for this entropy. Okay. Fine, and write down my equation as E equals to F minus dF by dt at constant NV. Yeah, into temperature T. Fine. So, I can write this also by taking a temperature derivative. Let me if I take a temperature derivative of F over T, so I get the first term as minus 1 by T square into F, but I want an F. So, what do I do is basically I multiply this entire thing with minus T square. So, you can see the first term would be minus T square into minus F by T square plus 1 by T into dF by dt. Okay. So, this will give me your right hand side. Okay. So, that is why I have written it like this. And so, you can now write down your energy E as minus kB T square d by dt of F by kBT, just multiplying and dividing by kB. Okay. And noticing that I can compute a derivative with respect to beta and convert into derivative with respect to t by simply saying that this is nothing but d over 1 upon kBT, which is nothing but I can take a kB upstairs, but a minus sign will incur and this will become a second derivative, sorry, this will become minus kBT into d by minus kb t square into d by dt. Okay. So, I can write down this noticing what I have just written E as nothing but d over d beta of beta f, okay, because 1 upon beta is nothing but 1 upon kbt. Okay. So, the operator minus kt square into d by dt is nothing but d by d beta. Now, you can compare this with what I have written here, yeah, equation 1. So, this is also an expression between relationship between energy and ln z. So, if I compare the right hand side here minus d by d beta of ln z with the right hand side here d by beta of beta f. So, I am calling this as equation 2, and just comparing 2 with 1 you can write down you can get one more bridge between statistical mechanics and thermodynamics. You can write down the free energy F is equal to minus 1 upon beta ln z. Okay. So, this is one more bridge that connects the microscopic world with the macroscopic observations, and all connections with thermodynamics start from this bridge. Now, you would be wondering what is the relationship between the energy that minimizes free energy and the average energy that I have just derived, which is nothing but the expectation value of the Hamiltonian. Well, I have already indicated that this E star is the same as E, but if you want to study this in more detail, see, this is the thermodynamic energy or the average value of the energy, and this is the most probable energy. So, these are interchangeable, because naturally if I leave a system with large degrees of freedom and wait for it to become equilibrated with the reservoir, and I ask myself a question that what is the average energy of the system. Well, I can very easily say that it will be nothing but the most probable energy, because the system would be spending most of its time near the thermodynamic energy, it will go above and below it. So, the most probable energy and thermodynamic energy are interchangeable, and this correspondence becomes even better as the system size becomes infinity. So, you can easily see that connection by some sort of an ensemble equivalence. So, the answer lies in the ensemble equivalence. Which simply says that as n goes to infinity, when you reach the thermodynamic limit, the canonical ensemble and microcanonical ensemble become the same or indistinguishable. So, the canonical ensemble that is the ensemble of NVT, converges to microcanonical ensemble, they become the same. And this is easy to understand. This means that if you take a system and increase the number of particles to a large value and thermostat it, as the number of particles goes to infinity, the energy of the system also becomes as good as constant. Of course, there is a small spread. What I mean to say is that the spread over mean becomes a diminishing number, and this can be proved by simply looking at the fluctuation in the total energy. So, I have already computed E, which is the average of the Hamiltonian, and that was shown to be minus d over d beta of ln xi, okay. And we have also, we can also compute what is the variance or width of the of energy. The variance would be the second cumulant of the Hamiltonian, okay. Now this is defined as the second moment minus square of the first moment. So the technique remains very similar to calculate it. Here I would simply take to compute the second moment, I will simply measure the average of the Hamiltonian square and to compute the square of the first moment, I will simply take the first moment here and square the entire thing, okay. And this can be very simply written as d square by d beta square, okay. I need a new page, so I will running out of space here, so I will write down this in the new page. So I can write this as so each derivative of beta will pull out a minus h, I need h square, so I will take two successive derivatives and pull out 2 minus h's. So this would be just divided by z, and here I will take just one derivative is enough to pull out a single h, and the entire thing squared. Notice that if I do a d over d beta, it will pull out a minus h. This is nothing but 1 upon z d square d beta square of z minus 1 upon z square d by d beta of z the whole square, okay. So now you can write this as d by d beta of 1 upon z dz by d beta. So the by chain rule it will give you the first term 1 upon z d square b d square z by d beta square minus 1 upon z square into dz by d beta the whole square, okay. and I already know what is the quantity inside the bracket, which is nothing but d over d beta of ln z. So, this is nothing but second derivative of ln z. Remember, I was computing the second cumulant of the energy. Now, we can actually see that this quantity here itself is a known quantity. Okay, so this is like the negative of the energy. So, I can write this as negative d over d beta energy or mean energy, and I know that d over d beta is a negative k T square d by dt. Okay. Since if you recall, d over d beta is negative k B T square d by dt. Okay. And finally, you can see that d by dt is nothing but heat capacity at constant volume. So, all these derivatives are at constant volume because we are doing a canonical ensemble problem. So, the heat capacity of the system at constant volume is nothing but it is related directly to the second cumulant of energy. So, fluctuations in heat energy in a canonical ensemble are directly related to heat capacity. So, fluctuations are important, they tell you something about the material property of the system. Fluctuations in energy are important quantities and they are related to property of the system. So, they are not they are very meaningful. So, how a system undergoes energy exchange with the reservoir and the nature of these fluctuations decide what will be the heat capacity. So, near a phase transition, for example, if these fluctuations become very large or diverging, the heat capacity of the system near such phase transitions would diverge. Okay. So, they are related to properties of the system in a very the connections are very deep is what I would like to say. Now, you can also see that this variance is scaling with system size, because heat capacity scales with system size. Okay, you can also see it here. So, I am going to write down this first. So, heat capacity is a property which is extensive, it scales with system size. Specific heat is intensive because heat capacity by N is specific heat, which is an intensive quantity, but heat capacity is extensive. You can also see here, I know that this guy E is extensive, it is the total energy 3 by 2 N KT, okay, scales with N, and beta is intensive. The entire quantity here is extensive, and so it is not surprising that we find our variance of energy or second cumulant of the Hamiltonian to scale with system size. So, I would compute the width or the standard deviation okay. So, let us so let us compute the width or the standard deviation. This is nothing but the square root of the variance So, this will scale as square root of n. And now you can compute the, like I was saying, compute the ratio of width over mean of the energy distribution. So, width over mean would width has already been so width is basically the width has already been computed here, which is square root of n, okay, and the mean is the energy itself, and I know energy scales as n because energy goes as 3 by 2 n kT. So, the width over mean will scale as 1 upon n to the power half and as n goes to infinity in the thermodynamic limit, this will go to 0. So, which means that my energy distribution, energy of a canonical system in thermal equilibrium with a heat bath, which was shown to be e to the power minus beta f e over the canonical partition function. So, this is the this is what I know from canonical ensemble. In the large n limit becomes a Gaussian distribution. It becomes a Gaussian distribution because energy is a random variable and it is a sum of energies of each particle, which itself is a random number. So, your sum of random numbers, a large number of them, gives you one value of energy, and energy itself is a random variable. So, you know, by central limit theorem, these random variables, which are themselves sum of large number of random variables, should be normally distributed. So, I am going to write it as e to the power minus e minus, or I can write it as, instead of this I can also write it as you know, I can write it as E star, okay, as you shall see that this is also E star divided by twice sigma square. Now, sigma square is basically our second cumulant, and I need to normalize this distribution. So, this is 2 pi sigma square square root, and there is a, this is a Gaussian distribution, okay. So, this is the canonical ensemble. Now, why does this become a canonical ensemble? It will be very clear. You see, this distribution, if I plot, okay, as n goes to infinity, because I know I need to invoke central limit theorem, I need to have large number of random variables which add up to a random variable which is normally distributed. So, I know from central limit theorem my n has to be infinity, only then I can invoke central limit theorem. So, I can compute, I can actually draw the distribution and understand what is going on, as you know, it is a well known fact that a picture is worth 1,000 words. So, let us sketch a picture here. So, this is our energy distribution, and this is a Gaussian that is centered at the most probable value of the Gaussian. So, I am going to call it as E star. But if I look at my distribution here, well, this distribution has a peak which is also at h bar. So, this is also equal to the mean value of energy, and whatever is the width here, which is proportional to I would say it scales as square root n. As n goes to infinity, my distribution actually moves on the right hand side, okay, it becomes wider. So, as a bigger n if I take, the distribution would be sitting at a value which is value of energy which is on the higher side. So, if I increase n, what would happen is the distribution gets wider, but the ratio of width to mean. So, suppose I say this is n1 and this is n2. I know this will scale as n. So, here the location of this would also scale as n. So, n2. So, the ratio of width over mean, here it was 1 upon. So, the ratio of E star over E star or H, the ratio of width over mean, which was going as 1 upon square root of n, is much smaller here. Okay. So, this means that the distribution gets wider, but what is happening is that the ratio of width over mean is now much smaller. It has also walked very far away on the right. The fact that it has become wider, I have shown the peak becoming smaller because I want to conserve the area under the curve. So, it gets smaller and smaller and gets wider and wider, but not only that, its location of the mean also gets far away from into the right, such that the value of the width over mean becomes diminishing in the thermodynamic limit, and eventually as n goes to infinity, this would be a sharp distribution further down the line. Okay. So, it would be like a spike, almost a spike, whose width is definitely larger than the previous two, but it is so far away on the right that the ratio of width over mean would be a diminishing number. So, eventually the distribution has a negligible. So, this would be eventually what you would get as you continue in this thing down the line, the ratio of width over mean, which is basically 1 upon square root n, which goes to 0. So, now you essentially recovered a microcanonical ensemble in the limit n tending to infinity, is basically the take home message. Okay. It is not the width alone that decides your property of the distribution, it is also the mean of the distribution. Okay. Suppose you have 100 rupees in your pocket, and the amount of your, let us say your expenses are related to the uncertainty or whatever the fluctuation of money in your pocket. Okay. So, suppose it is uncertain that you would have 10 rupees here and there over 100. Now, 100 is 10 is the square root of 100, but so 10 is what your expense would be if your income is 100. Now, suppose you go to if you raise your income to 1000, okay. Now, your expenses are, let us say, square root n, which is square root of 1000, which is Now if you compute your ratio of expense to your income, definitely in the limit of very large income this ratio would be a very small number, because let us say your income becomes 10 to the power 4. So, your expense would be 100, which is the square root of 10 to the power 4. So, the ratio of 100 over 10,000 is definitely 1 by 100, whereas the ratio of 10 over 100 is 1 by 10. So, 1 by 100 is much smaller than 1 by 10. Similarly, if your income becomes 10 to the power 5 or 10 to the power 6, so your expenses would be 1000. So, ratio of your expense over income would be 1 upon 1000. So, it became 1 by 10, 1 by 100, 1 by 1000. So, eventually it is not your expenses are growing. You would argue that my expenses are also growing. I was spending 10 when I was earning 100. Now, I am spending 100, but my income is also 10,000. So, definitely your expenses are increasing. I will not say that your expense, which is the width, the analogy of width, is not going to 0, it is increasing, but the ratio of your expense over your income is a diminishing quantity. So, I would say that you have no expense. As your salary becomes 10 to the power 6, if you earn $1,000,000 in a month, I would say that okay, you have essentially your expenses are 0. So, that is the analogy I have given here, that the width alone does not signify anything. It has the ratio of width over mean that signifies the nature of the distribution, and I argue that the distribution becomes delta function in the limit n tending to infinity essentially. So, here at this point I would like to break and take an example. In fact, I am going to do this problem with all of you, and this example is the familiar 2 level system. In canonical conditions. So, our 2 level system comes back, but this time it is in contact with a heat reservoir. This is not a constant energy 2 level system, it is a 2 level system where its energy can fluctuate, which means the number of particles in the excited state is a function that depends on temperature. Okay. So, our 2 level system is back, and let us remember the 2 level system. You had 2 energy levels 0 and epsilon for simplicity. Okay. So, you had 2 levels, and let us say you have some particles here and some particles in the ground state, and suppose I pick up any particle I, then Ni represents excitation, meaning that our Ni can have values either 0 or 1. Okay. So, 0 being it is in the ground state, and this being it is in the excited state, fine. So, I know that my energy of the total system can be written as nothing but summation over I Ni epsilon, and I will run from 1 to the total number of particles in the system. Eventually this will be nothing but N1e, okay, total number of particles that are excited in some sense, fine. So, what I am going to do here is instead of looking at this system from the point of view of energy, I will say okay, I do not want to adopt this procedure that I did in the case of canonical ensemble. I want to deal the system canonically. So, I will write down the canonical partition function. Why is this approach pursued? Because I have a system at constant temperature, its energy can change. So, our variable n1 is no longer a meaningful variable because n1 keeps on changing. Okay. So, that is why I do not want to do the problem starting with constant energy, because energy is no longer going to be constant. Okay. So, our canonical partition function, which is z nvt, if you recall, this is nothing but summation over all microstates e raised to power minus beta h mu. Okay. Now, our microstate for a given value of temperature is nothing but the specified values of excitations. So, means what is, it simply means that a given microstate is like, suppose I say that this is one microstate, this basically means that you can have your n1, that is the excitation of first particle, as 1, n2 as 1, n3 as 0, and so on, some specified values of these ni's all the way to the last value, which is nn. Now, this will give you a total value of energy, which is my h of ni. Now, these excitations will change between microstates. So, mu 2 may have different values of these excitations. So, n1 may be 0, n2 may be 0, n3 may be 1, and nn may be again 1. So, each microstate is a set of specified values of ni's in such a way that the temperature is T in the thermodynamic limit. Okay. Energy is not fixed anymore. So, you can actually make all ni's to be 1. This would be like all particles are in the top floor or the excited state, which we know is a very difficult thing to obtain, but in principle that realization is also allowed. There are no problems with that realization being allowed, is because the probability of that realization will be essentially 0 from statistical mechanics. So, the probabilities take care of themselves, we do not have to worry about it. Statistically a probability is still there, however small it is. So, microstates like this are basically nothing but a collection of these all these values of excitations. So, I can write down this summation as summation over all possible values of n1, n2 up to nn e raised to minus beta. Now, Hamiltonian is nothing but summation for the specified value of excitations. The Hamiltonian is nothing but summation I going from 1 to n ni epsilon, that is the Hamiltonian, right. If you have forgotten, you can write down the Hamiltonian of a microstate as nothing but the energy, which is summation I nie. Okay. That is what I have written here for the Hamiltonian. So, I can write this as summation all possible values. This will be nothing but e raised to minus beta epsilon n1 into e raised to minus beta epsilon n2, fine, because you have powers added up in the exponent. So, you have the ni's added up in the exponent, it splits up into products. So, I can now write it as summation n1 going from 0 and 1, n1 can only take 0 or 1, e raised to minus beta epsilon n1 into, these are all independent variables. So, these summations are independently applied all the way to summation on nn which is 0 1 e raised to minus beta epsilon n. Now, please look at these summations, they are all independent, which means I can simply take one of them and raise it to power n, okay, and which is nothing but if I take the values of n 1 0 and 1, this becomes 1 plus e raised to minus beta e to the power n. That is my partition function, that simple. Now, partition function is ready. You can connect thermodynamics with StatMech. So, with the partition function just recently computed, the first thing I am going to do is set up the bridge, which is minus 1 over beta ln z. This opens up the connection with thermodynamics. Okay. So, this is nothing but minus 1 upon beta logarithm of the partition function that I have just obtained as if I look at the definition, it is just n times logarithm of 1 plus e raised to minus beta e. Okay. As you can see, the free energy is extensive, it scales as n, because beta is intensive and ln 1 plus e beta is also an intensive quantity. The argument of ln is also intensive. There is only one quantity in the definition of free energy which makes it extensive, and it must be extensive. All energy scales are extensive. It scales as n because of this n. Okay. So, now I can compute the total energy of the system. The total energy is very straightforwardly computed, it is minus of d by d beta of ln z. Okay. So, you can write down this as minus n ln 1 plus e raised to minus beta e, fine. That is your internal energy, and okay. So, now you can recall that our free energy is connected to internal energy from this expression. So, I can compute what is my entropy simply I can write it as E minus F over T. Okay. E and F are both computed here. So, I am going to write down E and F as minus n by T into ln 1 plus e raised to minus beta e, okay, and minus f by t would simply be plus kb n ln 1 plus e raised to minus beta e. Okay. So, f is already minus 1 upon beta. Okay, so it is like yeah, if I multiply by minus 1 by t, so I just have a kb there. So, that is the expression for entropy. So, this ends the discussion on the 2 level system. So, when we meet in the next class, we will talk about the ideal gas as an example of a canonical ensemble. These two examples will together constitute a case for each degrees of freedom being discrete and degrees of freedom being continuous. So, the 2 level system is the discrete example for a canonical ensemble, and in the next class when we look at the ideal gas, we will take it as a case of continuous degrees of freedom, and I will show how you compute partition function in the case of a system which where the degrees of freedom are continuous. So, we break here and we meet again next class and we will take it from here. So, basically what I mean by the by this connection is that I want to derive some thermodynamic quantities from partition function. The first quantity that comes to my mind as always is energy, and I know the average energy of the system from statistical mechanics is nothing but negative derivative of logarithm of the partition function, like we just derived in the last discussion. So, this is nothing but negative derivative ln z is nothing but n ln 1 plus e raised to minus beta epsilon, and when you take the derivative what you get is minus n over one by 1 plus e raised to minus beta epsilon into minus epsilon into e raised to minus beta epsilon. Okay. So, this is nothing but n epsilon over 1 plus e raised to beta epsilon. So, this should ring bells with your previous encounter with the energy of the 2 level system in the microcanonical ensemble. So, as you can see here, as usual, the to basically to make the energy greater than n by 2. Okay. So, if I want to reach E equals to n by 2 epsilon, you have to make e raised to beta epsilon as 1. So, 1 by 1 in the denominator will give you 1 plus 1 will give you 2 in the denominator, and that will make the energy n by 2 epsilon, and the only condition in which e raised to beta epsilon becomes 1 is when beta tends to 0, and beta tends to 0 means your temperatures have become infinite. Now, this does not disagree at all with what I have discovered in the microcanonical case. Let us also so the conclusion here is that in 2 level systems maximum energy, so if you connect it to a thermostat, only at infinite temperature you can push more than half the number of particles in the excited state. So, maximum energy corresponds to half filled excited state, you can't exceed more than that. Okay. Okay, to push it beyond half filled requires temperatures more than infinity. So, that is clearly not possible. Now, a free energy here another very important thermodynamic quantity is nothing but negative 1 over beta logarithm of z. So, this is nothing but logarithm of z is nothing but n logarithm 1 plus e raised to minus beta e. Okay, which again as usual scales with n because beta is intensive. I can also write down entropy, which is nothing but from the first law of from thermodynamics I can write down entropy as E minus F over T, since you can write down E as E minus Ts as your free energy, Helmholtz free energy. Okay. So, substituting the value of E and F here, what we get is basically if I write down energy which is n epsilon upon 1 plus beta epsilon, e raised to beta epsilon, this is my energy minus free energy which is already minus 1 upon beta. So, I am going to write it as plus kBT n kBT into ln 1 plus e raised to minus beta epsilon, the entire thing divided by T. Fine. Free energy is already minus n k T into ln 1 plus e raised to minus beta epsilon, and so I can write this as n epsilon over T into 1 plus e raised to minus this is the final answer. So, you can write your answer in terms of beta n kb into beta epsilon. Okay. So, 1 upon T is nothing but kb beta, and I am going to take and the remaining is just n kb into ln 1 plus e raised to minus beta epsilon. Okay. And you can simply take n kb outside, what you get is nothing but beta epsilon over 1 plus e raised to beta epsilon plus ln 1 plus e raised to minus beta epsilon. Fine. So, this is the expression for entropy of the two level system, and this is where we end today's discussion on the two level system as a discrete degree of freedom example. In the next class we will look at classical ideal gas as another working example of a canonical ensemble. Okay. So, we break here and we meet in the next class.